Hello everyone and welcome back to this series on Diophantus. In video 3 we looked at some problems and noticed how Diophantus had to exercise some intelligence in how he assigned his one unknown symbol. Those problems were determinate, they had one particular solution. But most of Diophantus' problems aren't like that. As I explained in part 2 of this series, very often there are an infinite number of potential solutions, and Diophantus' challenge is just to find any one that involves distinct positive rationals. So, unlike modern algebra, which likes to keep things as general as possible, Diophantus' basic trick in these cases is to make very specific substitutions that reduce the problem to an easily solvable format. And it's really designing these substitutions that is the art of Diophantus' maths. As he describes right in the introduction to the whole work, the most common aim is to use substitutions to reduce the problem to an equation which involves just two powers of the unknown s, or as Diophantus put it, not powers but species of s. When you look at his practice, it's clear that the ideal case is where these powers are consecutive, and that's what I'm going to refer to, this is my term rather than Diophantus', as a helpful form of the equation, because it will immediately give you a rational value for s. So in this video we're going to consider how this works with a few fairly straightforward examples. As in the previous video, I'm going to show the problems that we'll work through, and I'd advise you to pause the video and think about how you would tackle them before we find out what Diophantus did. Right, let's start with this problem then. Find two distinct positive rationals whose product is 3 times their sum. Well, suppose we make one of the unknowns s. Now we're just going to think through the effectiveness of a couple of possible substitutions for the other unknown, with an eye on whether they produce what I'm going to call helpful form. So first suppose that the other unknown is some kind of constant. Then the product of the two unknowns is going to be that multiple of s, and 3 times the sum will be 3s plus a constant. So all the terms in the resulting equation will be multiples of two neighbouring powers, in this case simply s to the power 0, the constant term, and s to the power 1. So what Diophantus does specifically in this case actually is to assume that one of the unknowns is 12. Then we have 12s is 3 times s plus 12, rearrange, and we find a valid solution, 4 and 12. Now equally, Diophantus might have thought through a type of substitution of which he's actually even fonder than the constant substitution. Suppose the other unknown is some given multiple of s. Well, then the product's going to be a multiple of s squared, and the sum is going to be a multiple of s. So again, this kind of substitution is going to produce an equation in helpful form. The terms belong to the neighbouring powers s and s squared. Specifically, if we suppose that the unknowns are s and 3s, we're going to get 3s squared is 3 lots of 4s, and again we come up with that same solution, 4, 12, but by a different route. Now, there's certainly an element of good luck that these rather arbitrary substitutions actually led to an acceptable solution, so one that involves distinct and positive rational numbers. We could kind of try and rate them using modern techniques just for a moment. If we think of the problem as involving two variables, x, y equals 3 times x plus y, we can draw a graph of that. If I had to sketch it, I'd rewrite it in the form x minus 3 times y minus 3 is 9. And that shows that we're basically dealing with the shape of y equals 1 over x, but it's expanded a bit and shifted to be centred on the point 3, 3. So anyway, here it is, the graph. Diophantus' challenge is then effectively to find rational points on this graph where x and y are positive and distinct, so excluding the line y equals x, which I've put in red for the danger zone. So the first approach looks at the intersection of that graph with the blue line, y equals 12. And the second approach looks at the intersection with a line through the origin, y equals 3x. Now clearly in this case, the first method with the blue line was more liable to go wrong. If we'd chosen y equals 6 or some value below 3, we wouldn't have found an acceptable solution. Whereas we could have any line through the origin, any line of any positive rational gradient other than 1, and it would intersect the graph somewhere at a rational point that would give a good solution. And the use of these graphs also makes it obvious that either of Diophantus' methods would actually find all the possible solutions of the problem, but it would only do so one at a time, if you like, one substitution at a time. Okay, let's move on to the second problem. Same line of reasoning, roughly. We're going to split 16 into two squares. Each of those squares would have a rational side, or square root, as we would say. Now, if we think about the kinds of substitution we've seen so far, they aren't actually satisfactory. If we set one of the unknowns to s and the other to a constant, then the sum of the squares is going to have terms in s to the power 2, but also s to the power 0. And 16 is also another term in s to the power 0. So we're not getting helpful form. What about setting the unknowns to s and some multiple of s? Well, then the sum of the squares is going to be a term in s squared, but 16 is still resolutely a term in s to the power 0. So we're not getting helpful form either way. Well, in fact, if you think about it, we can't really make substitutions without having a term in s squared. So what we need to do to achieve helpful form is design a special substitution for the other unknown that's going to cause the terms in s to the power 0 to cancel, because s to the power 0 is too far away from s squared, which we definitely have, to create helpful form. So if the other unknown, for example, is 2s minus 4, or it could be 4 minus 2s equally, depending on where s is, we're going to get 5s squared minus 16s plus 16 equals 16. So then we can cancel the 16s, and we get 5s squared is 16s. It's in helpful form. We can just read off the solution of s equals 16 over 5. And we calculate 2s minus 4. It turns out to be both distinct from s and positive. So we've got a solution. Again, let's just think about this in terms of graphs. What we're aiming to do here is find a rational point in the upper right quadrant of the circle x squared plus y squared equals 4 squared, 16. Now, any such point is going to lie on a line that goes through the bottom of the circle, 0 minus 4, with a rational gradient. So involving the substitution y equals rx minus 4 for some rational r. And we can see by looking at the graph that that value of r must be above 1. Well, Diophantus used 2s minus 4, but changing the coefficient here instead of 2 would again produce all the possible solutions that there are, one by one. If we needed lots of solutions, we could get them. Well, we're actually going to see a very cute, completely different method for this problem later in the series. But just while I'm on it, of course, I have to mention that the general form of this problem, 2 squares adding to another square, is what inspired Fermat's last theorem. And that's famously supposed to have been written in the margin by Fermat. Fewer people know that it was the margin to this very problem in Fermat's copy of Diophantus. So we're going to try one more problem involving thinking about reaching helpful form, again with a slightly different kind of substitution. So this problem, find a square and a cube, both of rational side, such that the square of the square plus the cube of the cube is another square of rational side. So in this problem we've got some higher powers. In fact, cubes of cubes to the power 9, in other words, is as far as Diophantus ever goes. The square of the square looks like a 4th power, while the cube of the cube looks like a 9th power. So they're a long way away from being in helpful form automatically. So to achieve helpful form, we set the square to have a side which is a multiple not of s, but of s squared. Say it's 2s squared, then the square of the square is going to be 16 times s to the power 8. So we then need s to the power 9 plus 16 times s to the power 8 is some sort of square. Well, we're still aiming for helpful form, so what we do is we suppose that that square, whatever it is, we can make a substitution for its side as a multiple of s to the power 4. Say it's 6 times s to the power 4, we get s to the 9 plus 16 s to the 8 is 36 s to the 8, and we can immediately read off s equals 20 and reach a solution. Okay, that's about it for this video. Again, I've given you a few bonus problems here for you to try using the kinds of substitution that we've looked at, and this key principle of thinking ahead once you're thinking what kind of substitution will lead to an equation in what I've been calling helpful form, where all the terms belong to two neighbouring powers of s. In the problems that we've gone through, we've seen various types of substitution: constant, linear, non-linear. And one example, at least, of this important principle of designing substitutions so that certain terms cancel. That's one of the key principles. In the next video, we're going to look at another main principle from Diophantus for designing effective substitutions, and I hope you'll join me to see about that. Thank you for watching.